Welcome back, guys. So today we'll take a look at how to search a particular node in a binary search tree. Okay, so this concept is really easy, and once you study it, you'll think that what is the use of this, right? So this concept it will come really handy when you're solving some higher level problems based on trees. So on that note, let's start. There's something that you need to have before you start searching, and that is the key value. So you need to have a particular value that you are searching in a BST, right? So I just have integer values here. So I'll just say that I need, suppose I want to search the position of 7. Okay. So what I'm trying to do is I'll just, for now, let's think that all the values are unique. Okay. And what I'll return is I'll return the address of that particular node that has the value of 7. Seems fair, right? Because from if I the because if I have the address, then from there I can just I'll just print the data and the left child and the right child, so I can do everything. So I'll just return the address of that particular node. So done. Now let's start at traversal. So I've already mentioned this, that any traversal of a BST, it will always start from the root node. Why? Because the only address that we have of this complete tree, the only access point that we have, that is the root node. Okay, so everything will start from 8. That this is the root node here. Okay, so I am searching for 7 right now. Every time you compare the value of 7 with some value, there are only three possibilities, right? Either it may be greater, either it may be smaller, or either it may be equal. So if it is equal, then we are done, right? That is the answer. But what if it's greater? What if it's greater? Or what if it's smaller? So this is a BST, right? We have the advantage. We know that the root node will always be greater than the one that is on its left side, and it will always be smaller than the one that is on its right side. So let's start. So I'm supposed to find 7. I compare the value of 7 with my 8, my root node. Okay. So I see that 7 is smaller than 8. So what I do is I move to its left child. I straightly move to its left child. Okay. There are possibilities that 7 is not present, but we'll take a look at that also. But for now, let's just search. So what I do is I'll simply move to its left child, because if it's smaller, then it can only be the part of its left subtree, right? So we know that. Great. Now, now what I do is I compare the value of 7 with 3. So what I see is 7 is greater than 3. So if 7 is greater than 3, it only mean one thing, that if it is present, then it is part of its right subtree. So we are just narrowing it down, right? You can see that we are narrowing it down. After that comes 6. So we see that okay, the value of 7 is greater than 6, so it can only be in its right subtree. So okay, we move to 7, and yes, 7 is equal to 7. So yeah, that's all. We have found it our answer. So if I just have to write it, I'll just say that every time you compare the value, there are only three possibilities, and by now you know that either it is equal, either it is greater, either it is lesser. So if it's equal, then boom, we have an answer, right? If this is the case, then that is the answer. If the key value that we have, that is greater than the current node, then it means only one thing, that we need to go to the left subtree. No, sorry, if the key value is greater than the current node, then we have to go to its right subtree, right? And if the key value is smaller than the current node, than the root node, then we have to go to its left side, right? So this is the only concept that we need to search for. And by the way, before we start iterating this, every time we since we'll be using recursion, every time we start this, we just take a particular condition, and that states that we'll just take this. If the node is null, then it means that we are just searching for it, and we have just reached an endpoint, a dead point. So it only means one thing, that the node that we are searching, that is not there, right? So that was the explanation part of searching a BST. I'll just take another example for some better understanding, right? So that will help you all. Suppose what I want to search for 30, right? 13 seems fair. So 13 is greater than 8, and if it is greater, then what do? I move to the right side, right? And again I compare the value. What 13 is greater than 10, right? So if it is greater, what I do? I move to the right side, right? I move to the right side. Okay. 14 is smaller. Sorry, yes, 13 is smaller than 14. Sorry, 13 is smaller than 14. So what do? I move to the left side, and wait, this equal to our answer. So we have gotten an answer, right? So let's say that, suppose I want to find 11, and we know that 11 is not present in the tree. So again, let's start with the iteration. How do we do it? Really simple. 11 is greater than 8. Yes. Is 11 greater than 10? Yes. Move to the right side. Is 11 smaller than 14? Yes, 11 is smaller than 14. Move to the left side. Is 11 smaller than 13? Yes, 11 is smaller than 13. Then you move to the left side. But now this happens if node is equals to null, because now where we are, it does not have a left sibling, a left child, right? So it will return as a null. So that means that the value that we are searching, it's not present. So I'll just check a condition that if the node that was returned to me, if it is null, then the node that I was searching was not present, right? So pretty simple. Now shall we move to the coding part? Okay, so just give me a second. All right, now let's start with the coding part. So this is the same code that I wrote for the insertion video, right? I have not changed anything because I need to have a BST before I start the searching. So this is just the same BST, the same code. I've not changed even a single bit. Okay. So now let's start. By the way, this is my class node. I have only three values: the data, the left, the address of the left child, and the address of the right child. So done. Now let's start. I'll create a function that let's name it search. Okay, and I'll pass two parameters that will be root and key. Root will be essential because this is from where I'll start my traversal, and key is the value that I'm searching for, right? So I'll have my base condition as since this is I'm using recursion, right? So I need to have a base condition so I know that where do I have to stop. So firstly, the base condition will be if my root is none, which means that I have reached a dead end. Okay, so if my root is none, or otherwise there's another condition if my if my root the value of my root data is equal to key. So if this happens, then again, if in both of these conditions I return root. Why? Because if it's empty, then I return root. So I'll just check there that is my root none. I'll just I'll just choose that a condition. Otherwise I'll just print. If it's not null, then I'll just say that I have successfully founded my value. So that is one of my condition. Otherwise what I do is I check. This is the main condition that if my root dot data is less than key, which means that the value that I'm searching for is greater. So what I do is I'll simply call this function again. I'll just do a recursive call, and I'll just move to its right side. Okay, so I'll just give the address of its right child. Same. Okay, so it's pretty clear, I hope. So I just move to the right side. I'm just checking it in its right chapter. I'm just narrowing down my search, right? So otherwise, if this is not the case, then what I'll do is I'll just say return search root dot left, right? Otherwise I just move to its left side. So done with this. And by the way, I am following that procedure that left child is smaller than equal to the current node, less than root right child. Okay, so that is why I've just used else for my left side. So done with that. Now I need to just uh, let's create a temp variable temp. In this I'll store the temp the address that is returned to me. Okay, so temp, and I'll call my function search. I'll pass on the root, and let's say firstly I'll search for something that is present. So how about I search for 4, right? I'll search for 4. So I'll just check something. If temp is none, which means the value that they return me is empty. So if that happens, then I'll print that value not present. Done. Otherwise if they return me a value, otherwise they return me otherwise they return me something that is not none. So it only means one thing, that that value is present, right? So now let's start the searching, and I hope that I'll get value is present because 4 is present. Okay, so let's run our code. Yeah, so value is present, perfect, working. Now I'll search for 14, and 14 is also present. Okay, so run code. Value is present, great. And 141, let's see what we get if I print 141, because that's not present there. So value not present. Okay, so simple. And actually let's try something else. I just show you what is that I'm getting in return. So I'll just print my temp. Okay, not temp dot data, I'll just print my temp. I'm hoping that I'll get a I'll get the memory address. So I'll search for 14, and since it's present, I'll just print that am I getting the address successfully or not. So I'll just print it. And so you see that this is the address at where my current node is. Okay, so this is the address where my current node is, and this is the value that the root has of it. So this is how you iterate. I hope it gives you a more clear picture that how are you successfully able to move to the left side, to the right side, because some of you might get confused that what the hell are we doing. So this is how the compile, the interpreter there, it moves to a particular node. So this is the address that we have, right? Because only of this reason we are able to move. So I'll just show you for another node, because it's pretty fun. So 90, run code. Yeah, so do you see there's a difference between the address? You see it's 2060, and this is something like 2852. So they are not in a continuous order, they are randomly allocated anywhere. But how are we able to successfully traverse through them? Because we have that address, right? So this was how you search a node in a BST, and I hope you enjoyed it. So thank you for watching, guys.